All right. Well, welcome everyone to Neurosymbolic Wednesdays. We're back to regularly scheduled programming, presentations. So today we have Parth Padalkar on Interpretable Image Classification. But before we get started, maybe I'll ask for any other comments just to give people time to roll in. Comments from our town hall last week, which I thought was great. A lot of new ideas. Hey, Parth. Anyone on Discord want to add anything to last week's conversation? Anything we might have missed, or any new thoughts while we're waiting? In particular, as you've seen, we have this initiative around an Agentic protocol, and one of our commentators last week who joined the restream also is working on something similar. So I think anyone interested in this kind of topic, let us know. Oh, you guys are not seeing my slides?
No, I see a slide, but it's not in presentation mode.
Oh, okay. How about this? Yeah?
Now it's good.
Okay, maybe I'll get started. So, all right. So this is a little thing we made up based on our little Art Deco theme from the website. And here's the goal: we want to classify these images. We just made this up part, but we want it to be interpretable. So Parth is at UT Dallas, doing a PhD, and is going to talk about a certain thread over a few papers, including one at AAAI. And here's his website. If you want to find out more, we'll put all this, put these slides on Discord so you can get all this info. As always, comments, questions, go to these places. You can go to any of these places to post questions, and we will suck them up and they get over to me and or Olga, and then we'll answer them. Parth will answer them. And these are, in general, all the ways you can join us. The links for all of these things. And if you go to the website, you can find out about different specific ways to participate. This, again, is that project we're kind of ramping up. Okay, go to GitHub if you want. We haven't got any takers yet on this. People are shy, but if anyone wants to present one of these classic papers, then please let us know. This is reading group style, so it doesn't have to be your own paper you present. And these are the kinds of topics we have now, about 7 or 8 research threads. Maybe it's more people now. Maybe it's like 50 people working on different threads. So you can always jump in. Just email me. And I'll just leave this up for a second. You can see your topic here. And then we are hiring startups. If you want some visibility, might be able to get you a talk slot. And if you want to donate or volunteer, always welcome. Okay, with that, maybe I'll pass it to Parth.
Awesome. Sounds good. Hi, Alex. Hi, Olga. Hi, everyone. You can hear me, right?
Yep.
Okay. Let me share my screen and start the slideshow. Cool. See my slides?
Yep.
Awesome. Okay. All right. Should I dive right in or?
Yeah, go for it. Take it
Okay.
away.
Hello, everybody. My name is Parth Padalkar. I am a computer science PhD candidate at the University of Texas at Dallas. And today I'm going to be presenting my research on building neurosymbolic models for explainable AI, with the main focus being on interpretable image classification. And if we have time towards the end, I'll also sort of cover or touch a little bit on the topic of extracting predicates from large language models and doing some neurosymbolic modeling there as well for reliable reasoning. All right. So we all know that deep learning or neural AI is omnipresent in today's world. We have CNNs, VITs, large language models, and all these have become such a big part of our lives. The, they are also being used increasingly in sensitive applications such as self-driving cars, medical diagnosis. But the problem is that these models are black boxes, which means it is very difficult to get an explanation out of them. ChatGPT will give you an explanation, but there's no way to trust that explanation. There is another branch of AI, though, which has been around for a long time called symbolic AI. And these this branch sort of encompasses this logic programming paradigm, decision trees, automated theorem proving, fact solvers, etc. And the good thing is that symbolic AI is based on rules and solving systematically and reasoning through rules to reach a decision. So that is completely explainable. The good thing is that there is this branch of Neuro-Symbolic AI now that tries to combine neural models, which are better at pattern matching but poor at explainability, and symbolic models, which are better at explainability and reasoning but lack generalizability. So Neuro-Symbolic AI aims to combine both of these to see if we can get advantages from both of these paradigms in AI. Some examples: Google DeepMind's AlphaGo and AlphaZero are, well, they were not touted to be neurosymbolic models, but they were in spirit. And these models were essentially built for beating the game of Go and chess, respectively. So AlphaGo was made to see if the best human can be defeated in Go, and AlphaZero was made for a similar application in chess. And both of these models were based on neural models that were trained to find out how various patterns in these games could be learned. And at the same time, they had this Monte Carlo style search mechanism, which was the symbolic AI. And both of these mechanisms together made AlphaGo and AlphaZero one of the best models that Go and chess have ever seen, and they're still unbeaten. ChatGPT 5 is also loosely neurosymbolic because it has access to all these tools and APIs, and it has a Python interpreter also that it can invoke. So it does this neural processing because it's based on large language models, but it also has this support that it can take from symbolic reasoners like a Python interpreter, which is nice. So it's loosely neurosymbolic. And coming to my research now, my research is basically broadly dichotomized between creating interpretable neurosymbolic models for image classification and creating these fast and slow style system one, system two ideology of human cognition models. Basically, there's this ideology in human cognition that our mind is based on system one and system two, where system one does intuitive thinking and system two does slow, deliberate reasoning. So, this is another part of my research where I work with LLMs and logic programming to see if we can fuse this together to sort of um, replicate this system one, system two cognitive style in human cognition. All right. Creating interpretable NESI models for image classification is the first part of my talk. And before we get into that, we need to learn about a few background topics. First is the default logic, right? Default logic is a type of logic that can express rules that are true in majority of cases, but not always. For example, a typical rule would be birds normally fly, or by default, birds fly, but there are exceptional ones that do not. So if you look at this is a very general statement that a human would make about birds. We would say by default, birds fly, but there are exceptional ones that do not. Right? And default logic is very good at capturing these common sense style rules. And this is what the default rule for, or the default rules for this would look like. For example, this rule right now says, um, if X is a bird and not AB0X, AB0 is some predicate which determines exception to the bird predicate. And it says if X is a bird and some AB0 predicate, which is a normal case for X is not true, then X flies. This almost easily translates to by default, birds fly unless there are some exceptions, right? And the not here is negation as failure, but for the scope of this presentation, I'm just going to say that this is classical negation, right? And now AB0 is can be implied by a bunch of other predicates, like, for example, here, AB0X is true if X is a penguin and not some other exception to the penguin predicate. For example, AB1 could be a super penguin, right? So just to walk through the rules again and understand what they really mean, we are saying here that X is a bird. Well, if X is a bird and it's not abnormal, then X flies. And the abnormal case is that X is a penguin and it's not a super penguin. So essentially what we've captured here is that if X is a bird, which is not a penguin, unless it's a super penguin, it will fly, right? So this is a nice way to capture these defaults and exceptions. And we keep adding exceptions as we find them to refine our reasoning. So that's what default logic is. Now, the good thing is that default rules or default logic can be realized through a logic programming language called answer set programming. And ASP just gives default rules this operational semantics. For example, the same rules can now be written in this syntax where you've just replaced the implies with this colon dash, and the and becomes a comma. So it's the same thing again, but just the syntax changes. But now the good thing is we can pass these rules through an answer set programming interpreter and actually find values for X or do all sorts of reasoning. Okay, good. So why did we learn about default logic and ASP? Well, it turns out there is a very interesting algorithm called fold SEM, which can generate these ASP rules from tabular data. What that means is, and it does so with quite high accuracy, it's similar to what a decision tree would generate, but the rule set is much smaller. Hence, the rule set is slightly more interpretable. Here's an example. There's this famous Titanic survivor data set where you have a data set of people who were on board the Titanic when the Titanic sank. So there are various features for all the passengers, such as what was the age, the the gender, the boarding station, the ticket price, etc. And the objective is to figure out who perished. Right. So this is a simple classification problem, tabular data, and you can use polled SEM to generate rules and give some classification. For example, the polled SEM algorithm, when used on this dataset, gives two rules. The first rule says X perished if X was male, right? So the first rule straight up says that most males perished. The second rule says X perished if the passenger was a third class passenger, the passenger was female, and the fare that they paid was not less than 23.25, which means it was greater than 23.25. With just these two rules, we're able to get a 99% accuracy, 98% precision on that data set, which is really nice because this gives us a lot of interpretability. Good. One more piece of the puzzle, which is a CNN, a convolutional neural network. I know most people would be familiar with what a CNN is here, but just a very high level recap. A CNN is a convolutional neural network, a neural model which is often used for image classification. In this image, you'll see a lot of layers that form part of the CNN, and each layer has something called a filter or a kernel. A filter is an integral part of a CNN, and what essentially a filter is nothing but a matrix. A filter is a simple matrix that goes over the input image. So it will scroll through the input image while taking these point-wise multiplications and summing them up. For example, this is the input image, and this is what it looks like. Here it's represented in binary. So this would be the first patch over which the filter starts its striding. So the first patch, when the filter is on the first patch, the output would look like this 31 because it does these pointwise multiplications. So it goes 1 times 1 plus 2 times 0 plus 3 times 1 and so on and so forth. Summing that up together gives us 31. Okay, plain and simple. It will do this over all the windows that it goes through over the image. Okay, good. Why is this important? Because when the CNN is trained, every filter learns some concepts. And now this is where we get into the main idea behind my research, which is that the last layer filters implicitly start learning these high level concepts in images. What if we could learn rules for every class based on these concepts that the filters are learning? Right? That would be amazing because a CNN in itself is a black box model. Give it images, it will give you an output for the class of those images, but it's very hard to explain why it says what it says. So what if we could find those filters and extract rules from those filters in terms of the concepts that they represent? And that is exactly the point of the Nessie-Fold framework, which I created for generating these rules from a CNN and creating an interpretable neurosymbolic model. Good. And this work was presented at AAAI 2024. And here's the pipeline of how the framework works, right? We have a CNN that is given these input images, and the CNN gets trained fully on those images, all right? Now, what we can do then is we can extract the outputs of the last layer filters in the CNN, right? So F1 to Fn, for example, are the last layer filters. Remember, they learn some semantic concepts, so that's why we're interested in these filters. What we can then do is we can binarize the outputs of every single filter, right? So for example, if we have images of bedrooms, bathrooms, and kitchen, the first image, for example, here is a bed. We pass that through the CNN. We see what filter outputs we get. Again, filter outputs are matrices. So we'll take a norm and binarize those matrices such that the F1 filter would either be a 0 or a 1. F2 would either be a 0 or a 1. F3 would be a 0 or a 1. Now, the exact way to binarize this, or what we went with, was to define a threshold for the norms of these matrices, right? So once we have that threshold, we can then use it to binarize these filters. And what we get then is, for each image, we have a row of these binary values, 0 and 1, for each filter, which means we have now represented an image in terms of this binarized vector, where each dimension is a filter output, which basically means whether that filter is active or inactive, right? So the first row, let's say, represents the first image, second row, the second image, and so on and so forth. And now this is interesting because this is what the fold SEM algorithm needs, after all, to generate a rule set. So we've created this binarization table that we can pass to the fold SEM algorithm to generate some rules out of here, right? So once fold SEM generates rules, we already start seeing some semblance of explainability here. For example, the first rule says um, the image X is a bedroom if the F5 filter is active, the F1 filter is active, and not AB1, which are some exceptional filters or some abnormal filters that are also active, and some other exceptions, right? So we've got these rules now in terms of this answer set program, which is essentially defaults and exceptions for why a certain class should be classified that way. Okay, good. But still, the problem is I can read what the rules say, but I don't know what F5, F1, F41, or all these filters really mean. The good news is that, remember, every filter is actually representing concepts. It learns these concepts, and we can actually find what each concept is by looking at the activation maps for that filter, right? And based on those activation maps, we developed this semantic labeling algorithm that essentially will label each filter based on what it sees in the image. So now, for example, F5 after this semantic labeling becomes bed. So this F5 filter was mostly looking at beds in the images that we examined, right? And the F1 filter was mostly looking at pillows. And the F41 filter was mostly looking at sinks in the image. This is good because now we have given some semantic meaning to those filters. And the rule set now looks quite readable and quite understandable. For example, the first rule now reads, X is a bedroom if there is a bed, there is a pillow, and not AB1, where not AB1 is a sink and some other things. Right? So the rule says essentially it is a bedroom if there is bed, pillow, and no sink, which is how a human would also classify a bedroom. A human would go in and say, hey, this is a bedroom because there's beds, pillows, and no sinks, for example. Right? This is nice because now we've got this nice symbolic representation of the knowledge inside of a CNN. Good. And now we can use that CNN up till the last layer filters. Then we can populate the predicate values, the truth value of predicates, based on each filter's activation or deactivation. And that way, we can then classify new images. So the CNN plus the labeled rule set can be used for prediction afterwards. And since this is an answer set programming rule set, we have the SCASP ASP engine that can give you justifications as well later on as to why a particular image was classified as a bedroom or a kitchen or a bathroom or whatever class there is in your train set, which is nice because now we have a justification that is rooted in the operational way in which ASP is also interpreted. Good. Okay, so a brief overview of how the semantic labeling was carried out in this framework. Let's say we take a look at this F5 filter, right? We have these F5 filters activation maps that are overlapped with the images, right? So what we'll do is we'll find the images that most activate this filter, some top M images in this case, and we'll take the overlap of the filter's receptive field, or the area in which that filter mostly looks at, right? And once we do that, we have these nice masks over the image that tell us exactly which region this filter focuses on. And to a human now, I can start to see that this filter is really looking at structures that look like bed, right? But we need semantic segmentation masks to actually take a overlap or an intersection of the images with the semantic segmentation masks to figure out what each concept is in this region that the filter is looking at, right? So the semantic segmentation masks here basically mean that every single pixel in here is labeled with the concept that it represents. So every dark green pixel here, for example, is labeled with bed. Right? So when you take the intersection of the top row and the bottom row, you get these IOU scores, intersection over union scores, with various concepts and the strong overlap among them. So you see, most of them here are beds. The top concept is bed, so we go with labeling this filter as bed because that's what it seems to be looking at most of the times, right? And that's how the semantic labeling is done. Now, this requires us to have access to semantic segmentation masks, but actually now it's semantic segmentation masks are not that difficult to get because there are these open source, well, not open source always, but there are these foundation models that can give you the semantic segmentation masks for a couple of images. So if you want some explainability, the best way is to find some top 10 images, top 15 images, and figure out the semantic segmentation masks only for those images. Or you can even take a look manually through the top 10 images and give some concepts as a human to that filter so that you have some semblance of meaning associated with those filters. Okay, good. This is a rule set that was obtained when the CNN was trained on kitchen, bedroom, and bathroom images. You see, the first rule says X is a kitchen if there is a cabinet and not AB1X. The AB1X is again a bunch of other cabinets and bed. So essentially, this rule says X is a kitchen if there are cabinets and no bed in it, which is nice, which is also interesting because this is something that a human would also look at when classifying these images. And it's nice to know that even the CNN is looking at concepts that look like this. X is a bedroom if there is a bed is again another concept. X is a bathroom if there is a sink or a toilet in that image. And again, this is all extracted from the CNN itself. So we know that these are the concepts that it is looking at to make these classifications. And of course, this is a justification that we can get when we want to examine what is the class of an image and why that class was predicted based on these rules. Nice. So we ran experiments on a bunch of image classification data sets, and what we found out was that we get a 6% better accuracy than the previous state of the art, which was based on a decision tree implementation. And we get 83% smaller rule set size, which means that we can get better interpretability because there's not too many rules to look at and understand. But there's this limitations that also accompany, which is that there is a 12% accuracy drop compared to the vanilla CNN. Right? So the vanilla CNN does 12% better than our CNN plus the rule set. Because what we've essentially done is that we have binarized the filters in the middle after the training was done. And that causes a lot of information loss. So we noticed that this is what was happening, and this was causing a lot of information loss. So the next idea that we came up with was that what if we binarize those filters while training itself, right? And it turns out there is a way to do that, and we can then get the accuracy gap to reduce from 12% to 3% between the vanilla CNN and the CNN plus the CNN plus the rule set. So the gap now narrows quite a bit. Good. So this is for the CNN. Can we do this for a vision transformer as well? Is there a way to extract these rules from a vision transformer and then use those rules to classify and hopefully get some explainability out of them? Well, the fundamental problem with a vision transformer is that there are no filters in a vision transformer. So there's nothing to binarize, there's no feature localization. However, there's this class embedding vector that is available. And just to give you a brief recap of how a vision transformer works, this is the vision transformer architecture. And a vision transformer will take an image, it'll slice it up into various patches, and it will pass those through the input layer. So all these patches go through the input, and there's this extra embedding or class embedding vector that essentially, as it propagates through the vision transformer, aggregates all information from every single vector here that is necessary to classify that image as whatever. Good. So now the interesting thing here is that we have this class embedding vector available, and this has all the information we need. So what if we could extract the semantic information from this class embedding vector now, right? And this has been explored a bit in terms of LLMs with sparse autoencoders. So we use a similar idea here where we added another linear layer that is a sparse concept layer that has neurons, which could then be binarized, right? So the whole idea is that we want a layer that gives us outputs that are as binary as possible so that we can use those outputs as input to fold SEM to generate a rule set. Good. This is the framework, the NESI VIT framework that we came up with, and this was published in ICLP 2025. And notice that the structure overall looks very similar to what we had in NESI Fold, which was the CNN-based framework. The VIT is all the images are input to the VIT to train it, and we extract this class embedding vector from it, and we use this sparse concept layer, which takes this class embedding as input and outputs these binarized, well, pseudo-binarized values, ideally, where each neuron would give you a value between 0 and 1. And then once we have these values, we don't have to calculate any threshold. We can just binarize them at 0.5. So every value can just be binarized at 0.5, and we get a 0 or a 1 for every single neuron. And once we have that, we can then use the fold SEM algorithm to generate this rule set, and we get the labeled rules in the end, which is nice. But there are a few problems here. We have 3 objectives that need to be met in order for this to work. One is that similar vectors, there should be similar vectors for similar images that are an output of this sparse concept layer, which means if I have bedroom images, then the sparse concept layer should output similar-ish vectors for all the bedroom images, such that it's easy to segregate them in some high dimensional space, right? Then the output values should be as close to 0 or 1 as possible, so that when we just do a 0.5 thresholding, there's as little information loss as possible later on. We want during the training itself, the values to go between 0 and 1 and to the extremes as possible. So every value should be as close to 0 or as close to 1, right? And the third thing we want is only a few neurons should activate, leading to these sparse vectors, which means if we have very few neurons that activate, we can sort of have a very small concept set for each image. So the rules that we extract would be very succinct and small because we need very few concepts to identify a particular image. So these are the three objectives that we need to that need to be met in order to achieve a good classification accuracy, for example. Good. Turns out that for the first objective, there's something called a supervised contrastive loss, which can directly be used, which pushes similar vectors together and dissimilar ones away. Very nice. Then for the second one, we designed this entropy loss, which basically just penalizes values that have high entropy, which means whenever a value has, whenever a neuron output is close to 0.5, that's very high entropy. So it penalizes it and it makes it go towards 0 or 1, which is what we want. And we also added the sparsity loss, which means that every vector that is generated should have as few neurons active as possible, such that we have very few concepts that would represent a particular class, which is good, which is what we want, so that our overall rule set size remains as low as possible. We can then use a weighted sum of all these losses and do the training. And without going into too much details about the losses themselves, what we get is very interesting. Once we train this Nessie VIT framework, and notice that here there is no post hoc binarization. Everything happens in the training itself. We see that there's a 6% increase in accuracy over the vanilla VIT in addition to an interpretable rule set. What that means is the vanilla VIT does slightly worse than this VIT plus this rule set because of all the mechanisms that we used for binarizing the vectors and making sure that each value is as close to 0 or 1 as possible, so that fold SEM can do its job and generate well segregated representations and rules. The downside of this, though, is that once we have this sparse concept layer, we're essentially relying on these neurons to indicate what concepts are visible, available in the image. And these neurons aren't like filters. They're not matrices. So they can't capture those concepts very well. So we tend to lose a little bit in terms of how clear each concept would look like, right? So we lose a little bit there, but we do gain in terms of accuracy. And again, this is ongoing work, and there can be a few things that could be done to ensure that each neuron strongly learns to associate with attention maps that look at various concepts. This is something that I'm working on currently and hopefully gives some good results there. But this is also pretty good because now we have a way to get this rule set out of a vision transformer that can at least give us a point to start off with, right? Good. So what do we do with this interpretability? We have this rule set. What do we do with it? The idea is the rule set can be scrutinized to identify biases. Specific filters in the CNN, for example, can be targeted to either unlearn or learn the desired or undesired concepts. For example, consider this rule set here that looks at street and desert road images, right? Now, this is the CNN. We extracted a rule set from it, and notice what the first rule says. First rule says X is a street if there's a building, which is fair. So it's looking at street images and classifying them based on whether there's a building in the image or not, right? The second rule says X is a desert road if there is sky in the image. which is intriguing. The CNN has learned that there is always sky in desert road images because most of the desert road images have a vast expanse of sky in them. So the CNN is learning to classify desert road based on whether there's sky in the image or not, which is slightly problematic, or which is not what we would want the CNN to do. We would want the CNN to critically identify a, a very representative feature of a desert road, like the sand or the ground, or that it's a desert, right? So what we could then do is we could then identify desired and undesired concepts. For example, for the street class, we have sky and tree that are undesired. For the desert road, sky and building are undesired. For the street, the desired concept is a building. And for desert road, sand, ground, or desert are the desired concepts. And now the idea is, can we make the CNN in a targeted way forget the things we do not want it to remember? Like, can we make the CNN forget that there is sky in desert roads, and make it lean towards the sand, ground, or the desert that actually is there, usually in desert road images? Turns out we can do that because we have every concept linked to a filter, and a filter is nothing but a matrix that can be flattened to create these nice concept representation vectors, right? So every building filter can be aggregated together to create this concept representation vector. Every ground vector, for example, can be aggregated to create this ground representation vector. And we can create all these vectors for every concept that is desired and undesired. What we can then do is use this semantic similarity loss that we created, which is based on um, finding the cosine similarity between the desired, between the bad concepts or the undesired concepts and all the filters in the CNN, and trying to minimize that while trying to maximize the similarity between the good concepts and the filters inside of the CNN. So essentially, we're trying to push the CNN filters away from the bad concepts and go towards the good concepts for each class. What ends up happening then when we retrain the CNN is we get a rule set that now looks like this. Notice that the street is still being identified by building. We have desert road now that is being represented by the ground and the road in the images. We have, well, the CNN has now forgotten about sky. So we have penalized the filter so much that it has now forgotten about sky, and it has learned the desired concept that we wanted it to learn, which is nice. And now we can be sure that it is not biased towards a concept that we did not want it to learn. This we call the Nessie-Bicor framework, or Neuro-Symbolic Bias Correction Framework, and this was published at ICLP 2024. This is what the pipeline looks like. We have this CNN that has been trained with certain biases, and what we can do is we then extract the various concept representation vectors, and we calculate the semantic similarity loss. And every k epochs, we generate a rule set, see what undesired or desired concepts are there, compute the representation vectors for those concepts, calculate the semantic similarity loss, minimize that loss, retrain the CNN again. That way, we forget the things we do not want to remember, and we try to learn things we do want to remember. Good. So a very small portion as an added bonus is the second part of my research, which is based on creating these fast and slow models for better reasoning and reliability. The idea is that we can use an LLM for extracting information and use a logic program to do the reasoning afterwards, right? For example, we have Joan found 70 seashells on the beach. She gave 5 to Sam. How many does she have now? This question is a question that requires a certain amount of reasoning, and LLMs are not very good at reasoning, as we know. So the idea was, then let's extract things that we would need. For example, predicates like this: has Joan 70, transfer Joan Sam 5, has Joan X. These are all the predicates that we would need in order to give to a logic program that we've pre-written to solve math problems. That logic program can then be executed using some logic programming interpreter, and we get the answer from there. So essentially, this way of using LLMs for only extracting information that is required forms the system one side of human thinking, fast, intuitive, and the logic program forms the slow, methodical part of human thinking, right? And these two can then work together to give us answers. And we called this the STAR framework, and we used it to create these reliable chatbots that can give you answers based on very fixed domain queries. For example, we created a bot that would suggest restaurants around the UTD area, the UT Dallas area, and you could ask it things like, I want something that is family friendly, I want something that is cheap, or something that's this far away, and it will understand you because it will create these predicates in the back end, and the logic program that we had written would do the reasoning and give you accurate answers every time. So what we found out that was, in a narrow domain, you can have 100% accuracy. Although if you want to scale it, you would have to come up with the logic program yourself, you'd have to write it. But that's the trade-off here that we decided was a good one to have, because we get this narrow domain 100% accuracy. We published this at ICLP 2023, and an extension of this could very well be that the LLM itself generates the logic program and has a way of verifying whether that program is correct or not, and then uses those errors to again generate that logic program, a new one, and then the logic program can be used to do the reasoning uh, via separate interpreter, and the LLM can still be fixed at only taking out the relevant information from the text. That way, we have this nice neuro and symbolic synergy to solve complex reasoning problems. Some future directions that I'm very interested in looking at is improving interpretability in LLMs, where what if we could find these ground concepts to groups of neurons in LLMs? For example, if we could find certain neurons in the LLM that represent things like hate speech or war or things like that, which could be problematic. And what if we could mute them directly, right? What if we could mute those concepts then and there using a representation that is linked to those neurons, and have them such that they cannot be fine tuned, or those values could not be changed, right? This would be very interesting, because then that has applications in jailbreak prevention, for example, in LLMs. If you have identified a bunch of neurons that are ground to particular concepts and that cannot be moved or shaken, that would be a very interesting direction to pursue based on the research that I've done, where I can identify these particular neurons and the concepts that they represent. Another interesting direction would be to see if we could extend this STAR framework to fast and slow architecture for planning, where the STAR framework dynamically uses the LLM to generate new rules based on whatever the environment throws at the agent. And the rules then sit somewhere else in memory, and a symbolic solver does the reasoning while the LLM does information extraction. That way, the um, planning problems could be better solved, and it could be potentially very applicable to robotics domains. Another direction would be to create a probabilistic answer set programming paradigm, where you have these probabilistic rules that can be very tightly integrated with any CNN or a VIT during the training itself, right? That way, this 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 rigid nature of the rules that we have right now won't pose as much of a problem in terms of this accuracy loss that we see, and the training could be more fluid. That way, we can do better common sense reasoning as well, because that's what answer set programming is mostly used for. It's used for common sense reasoning, and goal directed answer set programming gives you justifications as well. So, reasoning under uncertainty could be very, very um, could be a very useful application with a probabilistic answer set programming paradigm. To conclude, there are these there is a push these days, right, towards creating AI that is capable of explaining its decisions as well as able to employ systematic reasoning at the same time. And it's very difficult to manage this along with accuracy. There always seems to be a trade off. But through my research, I've tried to take steps towards making AI models more explainable and correctable with the Nessie-Fold, Nessie-VIT, and Nessie-ByCore frameworks. And the STAR framework is a step towards complementing neural AI with reasoning abilities. And there's a lot of interesting work to do, and excited to collaborate with anyone who wants to uh, take a step towards one of these objectives. And I'm always happy to chat and talk about things that could lead to such progress. And also, I'm on the job market for a faculty position or research positions, and would love any pointers or any jobs that anybody would have available with them. Thank you so much. That was my presentation. I would gladly take any questions that you might have.
Oh, great. All right. Thanks, Parth. Great talk. We have some
Thank you.
questions. Olga, do you want to do the questions?
Yes, sure. Okay, let me take a look. Okay, just some comments that you are the best out there to explain all this. And I kind of agree with this. Great, clear explanations. Okay,
Thank you.
question. Are there SSMs generated by your algorithm, or do they need to be presented beforehand?
Sorry, are the what? Sorry.
SSM?
Yes. So they do need to be presented, but as I said, you need a very few images that need those semantic segmentation masks. So you can either do it manually, or you can have a foundation model that can be used to create these very few SSMs, but you would need these semantic segmentation masks. Otherwise, you could even manually look at the feature maps that each filter generates and see what concepts it's looking at, and you can just manually label those.
When you say a few, what do you mean by a few?
So it depends, right? For example, we did some experiments with what happens with particular values of a few. So we took 5, 10, 15, and we saw how well the concepts adhered to the filters when we increase the values. So what we saw was, if we take like 10 images and we label the concepts based on those 10 images, then we have a reasonable enough adherence that the filter shows to those particular concepts, that it doesn't show anything else overall in the explainability.
Okay, thank you. The next question is, how does this work with adversarial input? The rule just doesn't apply in this case?
With adversarial inputs, if your if your model has been if your model has been trained with a particular type of images, then it would only do what the CNN would do anyway, or what the VIT would do anyway. You will just know what rules fired to reach that conclusion. So if your VIT or CNN was susceptible to adversarial attacks, you would now know which rules fired that led the CNN or the VIT to make that decision. And then if it's adversarial, it's adversarial. But you'll only know what happened within the model to classify that image as whatever class it classified it as.
Okay, thank you. The next question is, seems like these and Settlian machines are a good match, since these are binary in principle. You don't care about binarization. It's like more like a comment rather than a question, but do you have anything to comment on this?
I think the only reason why binarization here is necessary is because to get a symbolic grounding or a symbolic rule set, you always deal with predicates that have truth values associated with them. So it's always nice to have this binary representation in the CNN that can be directly linked to truth values, for example, of predicates. And that is a nice way for humans as well to understand whether something was true or not, present or absent. So that's the only reason that the binarization is there, to make it more intuitive to look at the rules and understand them.
Okay, thank you. There are a few more comments about how good your explanation are. Explanations
thank you.
how everything is simple. Yes. Okay, let me see what we have.
If you're a university, you should hire this guy.
Yeah.
Good teacher.
Okay.
I hope so, yes.
The next question is, okay. We see a question on here. Thanks for the great presentation. I'm curious to know if you have utilized any dimensionality reduction techniques for classifying vectors from hidden layer.
That's an interesting question. I haven't looked at any dimensionality reduction techniques yet, but the idea behind using a sparse concept layer was that the embedding vector that we get is already very dense. It has a lot of information packed in it, and if we can extract that information in a higher dimension, such that each neuron can be monosemantic, for example, if hopefully, ideally, every neuron in that layer can represent one or a few concepts possible, that would be amazing. So I don't know if dimensionality reduction would help, because we need to go towards monosemanticity, and that can only be achieved by extrapolating out the embedding vector into a higher dimension, so that we have neurons that become monosemantic eventually. But it could be, I can't think of any way to incorporate dimensionality reduction, maybe to make the vector even more potent with information. Perhaps that's possible to do. But yeah, it will be interesting to use any dimensionality reduction techniques there. Yes.
Thank you. The next common question is, congratulations, Parth, really nice work. Just as a matter of curiosity, which language are you using to implement the reasoning part of your mode?
Yes, so I'm using answer set programming, which is Prolog based, but with negation as failure. So it's very similar to Prolog. And I am, on the other hand, using something more specific, which is called goal directed answer set programming. Answer set programming in general is known to not have reasoning traces, but with goal directed answer set programming, you can get these nice reasoning traces as well, and at the same time have benefits of using this negation as failure, which is very useful in common sense reasoning. So it gives you the best of both worlds, because with explainability you get this nice reasoning trace, and you also have the highly expressive power that you get with negation as failure. So yes, I'm using answer set programming, but a variant of that, which is called goal directed answer set programming.
Okay, thank you. There are a couple more comments. I'm not sure if you have more questions. One second. Did you encounter a cyclic restriction in your case as well? And if so, how to proceed for cyclic identification?
Could you repeat that question? Sorry, I couldn't hear you.
Did you encounter a cyclic restriction in your case
Okay.
as well? And if so, how to proceed for cyclic identification?
That's a good question. So Fold SEM, the algorithm, it generates a stratified answer set program, which means there are no cycles inherently that can show up. But yeah, so because there are no cycles that show up, because of the nature of that algorithm, I don't have to deal with any cyclic cases. But of course, answer set programming can handle cyclic cases. Just for the sake of keeping it simple, I think it is necessary to have just stratified rules that can be easily read and not have too many complicated cycles.
Thank you. Okay, let me also check the Discord if you have something there. Okay. Yes, there are a couple of questions on Discord. There was a similar talk and Neurosymbolic Summer School 25 focusing on features. For example, the color red for an apple. What is the advantage of your approach using higher concepts in your opinion? And then there is second part of this. Speaking of compositionality, there is not so new approach to translate the clever data set into objects and their relations between them in a prologue-like language. Could it be promising to construct the representation of the worlds bottom up as does our visual system? So maybe it's like, yeah, two questions from the same person.
Yes, that's a very interesting question, the second one, which is creating these rules bottom up. That is a very interesting approach. And I know that there are a couple of works that aim to do that, where you find multiple concepts and you try to sort of hierarchically cluster them until they reach bigger and bigger concepts. Uh, I the only way that I can think of that happening is if we could somehow leverage the other layers in the net. In the model, if we can figure out what the deeper layers or the earlier layers are learning and segregate those concepts and sort of have a symbolic representation for each layer after that. That way we can do this hierarchical clustering to build those concepts from ground up. That is one thing that I can think of, but that's a very interesting direction. I have not explored that much. Yeah.
Thank you. Yeah, the next says very off topic, so yeah, treat as this. What do you think of the paper, efficiently updatable neural network based evaluation function for computer shogi? If you know anything about this paper at all, this was a big paper for all neural network applications in games, and the core idea behind NNUE was about interpretability back in 2018, but I feel like this paper is not being discussed a lot. So if you have anything to comment, if you heard about this paper.
I don't think I've heard about this paper, or I might have, but I don't remember. But yeah, there is a lot of work that is going on in this area, as we all know. That's why we have these Wednesday talks every Wednesday. So many people doing so many things. But yeah, I'm sure that would be an interesting paper to read, but I don't think I recall reading it.
Any paper like that somebody feels really has a big insight in it that maybe is not discussed enough, or you feel people should know more about, is a good candidate for someone to present. You don't have to be the author. 2018 is not that long ago, so we might actually reach out to the author. But if we don't get them, then it's fair game for someone to present. So keep that in mind. Anything where you're like, everyone should know about this. I think, please propose it to us.
Okay, thank you. The next question is, quick question. Is it possible to share the presentation slide deck? Parth, if you don't mind, we will share your slides on our Discord.
Sure. Yes, for sure.
Okay, the next question is, what about binarized neural networks? Can you create a rule set over the last layers of binarized classifier?
Yes, that's a good question. The only thing is that the binarized neural network doesn't have an inductive bias towards classifying or towards capturing concepts like a filter does, for example. A filter is it is created to capture concepts inside of a model, but a binarized neural network, on the other hand, doesn't really have that inductive bias. So I think better would be to have like a CNN or a VIT plus a binarized mechanism integrated together, like what I've tried to do. But maybe binarized neural network insights could be very useful to create this hybrid structure and then extract rules from there. So that's a great idea. Yeah, I hadn't thought about that.
Okay, thank you. And the last question so far, have you looked into reverse engineering 3D shapes into CAD operations? So geometric manipulations based on shapes, which could eventually lead to solving tasks where you find solutions based on multi-modal constraints, which itself could be generated from something like create a part that attaches to this object and is able to be 3D printed. Might be a bit out of distribution, perhaps.
Wow, that's a great idea. I have not thought about that, but that really seems like a very good idea. I haven't ventured too much into multimodality because my focus is on creating these interpretable by design models such that we have a separate model that does good accuracy and explainability at the same time and can be viewed as an add-in replacement to a vision transformer or a CNN. But that is a great idea, and maybe sometime we can collaborate and do it as future work.
Everyone interested, please reach out to Parth for collaboration on all these great ideas. Okay, one question that I have. One second. You mentioned that you have thoughts of improving interpretability in LLMs, but did you think of applying something like this to minimize biases, not only like in CNNs, but in LLMs, like in some classification tasks, like should a particular bank give this loan to this person, and to minimize biases in this modeling, like outside of CNNs, maybe applying similar techniques to what you applied to images to minimize biases in other areas as well.
Nice. Yes, yes. So this is part of the future work that I have planned, which is using this to identify biases and correcting them in LLMs. I think a lot of it could be transferred to LLMs. All we have to do is find these concepts that are linked to neurons in some representation. It could be a latent representation such that there is tight coupling of those neurons with that concept. If we can identify neurons that are very tightly coupled with those concepts, then it would be very sensible to curb those neurons of the biases that they possess, or just clear the concepts that they are learning to represent, for example. That could be something that we could do. And yeah, that is something that I have planned for future.
Okay, nice.
Olga, there were a few early questions I think we didn't get to.
Okay, sorry if I missed it.
I can do them.
Yeah, thank you.
So I could build the abnormal set with ORs, right? As in ostrich X or penguin X and not abnormal X.
You could do that. You could build it with ORs. It's just that the algorithm that I use, it does it this way, and because it gives a much cleaner representation. That's the only thing that's the only reason why I chose to go with this, and it fits nicely with the goal-directed ASP paradigm that I use. Uh, that's the only reason I'm using this, but I think you could do it that way as well. Yes.
But how is fold SEM better than decision trees? Seems to be the same approach, basically, just a different notation.
Yes, it in terms of accuracy, it's very comparable. It only generates a much succinct rule set, and it has the added benefit of generating a rule set in an answer set program notation, as you said. Yes. So in general, the rule set size is lower, uh, and it gives you a direct ASP notation that you can plug to an ASP interpreter and just get going with it. So that's the only advantage that you have. But it's very comparable to a decision tree, yes, in terms of accuracy.
Can you please tell if association rule mining is related to fold SEM?
Yes, association rule mining is very related, yes. Uh, but I would say that fold SEM works more closely with the principles of how a decision tree works. Association rule mining is like, well, again, it has a lot of flavors, and I'm sure one of them could be how a decision tree also works. One thing that I can think of is that you need tabular data for fold SEM to work or a decision tree to work. I think association rule mining could be done with just your bunch of predicates that you have and bunch of rules that you have in your knowledge base, and then you can find associations among them and also generate rules there. So it's just, I think, a different flavor of association rule mining that fold SEM and decision trees also use.
Olga, did we do question 5 in the private chat?
Okay, there are too many channels I'm monitoring. I'm not sure. 1 second, let me take a look.
I want to make sure we
Yeah.
got to everyone.
Yes. Okay. I'm not sure if Parth knows about our presentation at the summer school, but I can ask this question again. So there was a similar talk at the Neuro-Symbolic Summer School 25, focusing on features. For example, the color red for an apple. What is the advantage of your approach using higher concepts, in your opinion?
Yes, I think this approach is more based on finding these representations from um, from the connectionist knowledge inside of a neural net. Can you find these concepts from inside of a CNN or a VIT and use them in a rule set is more the ideology behind this. And the the next direction where this could go is to see how fine grained can we get. Can we actually find object parts as well as the high level objects, and to what degree of accuracy or granularity can we do that is the next step to go from here. But I think the direction that I'm going is more top down, where you have these high level concepts that you just cleanly put in predicates as part of rules, and then you reason, or then you just look at them and understand what they mean. If you want more granularity, one thing you could do is maybe look at the earlier layers in the network and figure out what other concepts you can find.
So here's some more potential collaborators for you, Parth.
Yes.
Parth, there are some ways to do dimensionality reduction without losing information. I can send you a link to a paper if you're interested.
Oh, perfect. Yes. I would love to read that.
I've seen things like that using sparse autoencoders and language modeling to train a second model to classify the activations of the main language model. So I know it's possible to do this with a CNN. And given the Platonic representation hypothesis, that you could use a VLM to assist with the labeling of the features in a CNN.
Oh, nice. Okay. That's good to know. I'll take a look.
There's also some interesting work on geometric deep learning. That is a more recent field with a lot of work in interpretability. Maybe means not with a lot of work in interpretability.
Also, someone asked if Parth, you're okay with sharing your contacts, because someone has some concrete ideas about hierarchical clustering and wants to contact you. So I'm thinking maybe while we are speaking, Alex, maybe you can share the slide with Parth's information again with his website.
Yes.
Yeah. Okay. And one more question. No data set is perfect regarding image classification. Could logic help detect candidates for manual review? If so, how?
For manual review, I'm not. Well, I think it could be possible, but I don't know. I haven't thought about it that much. Yeah, I don't think I have any answer for that right now, but my hunch is that it is possible.
Okay, thank you. By the way, here is Parth's information, his site. So everyone interested, probably you have contacts on your site, right, Parth?
Yes, I do. Yes.
Yeah, so everyone interested can go to Parth's site and reach out to him. Okay, another question. There are major drawbacks to Boolean logic. For example, what is a gradient of a step function? There are also now far fewer possible states, and on complex data, this would likely hurt accuracy.
Yes, that is a good point. And yeah, that is true. That's why I think one direction that I want to go is create this probabilistic representation for ASP, where the predicates are probabilistic and they're not completely Boolean. So we can have gradients flow from the predicates all the way back to every neuron in the network. And yeah, I agree. That is a problem of any rigid rule-like mechanism that you're using to explain your model, for sure. Yes.
Thank you. And I think so far these are all the questions, unless I missed anything else.
Cool.
Okay.
Yeah, I have so I'm just curious, Partha. So you when you I think you showed a really nice kind of result where about the desert road and the sky. This is similar to the classic adversarial robustness thing of one pixel change on a stop sign makes it a giraffe or whatever. So I think but are you assuming there's a human in the loop that post checks the interpretable rules and and then feeds back into then there's some retraining. So there's some kind of I mean, is it an actual interface, or is it actually during training, like there's a human actually in the loop of training, or are you just kind of suggesting this could exist?
Yes. So there's no human in the training as such, but what, for example, I did was you can get some background expert domain knowledge as to what concepts you would want and would not want, for example, to show up. And then you could have a list of those concepts, and just based on them, whenever in the training you find these concepts appear in the rule set, you can flag those and add them to the loss that will penalize the filters from going towards that concept if it's a bad concept, or it will make sure that it goes towards that concept if it is a good concept. You can have this list of concepts that are desired and undesired, and you can then train in a loop. Yes, and there's no human needed as such. Only you would need it if for the expert knowledge, basically. That's when you would need the human.
What would be an example of an undesired concept?
Yes, for example, the sky concept was undesired in desert roads. You
Oh,
did
okay.
not want the sky to appear.
Oh, okay.
Right.
If you, all right. But presumably you only don't want sky because it's desert road, but
Right.
it would be hard to specify up front. I don't want any concept in the whole system. In the whole system, I don't want sky to appear ever. I mean, so you'd have to examine the rules.
Yes.
I
Yes.
would
So
think.
once you have the rules from
That,
a CNN that you can generate, you can then look at them and see what looks right and what doesn't to a human or a domain expert. And then based on that domain expert's knowledge, you can inject this knowledge essentially into the CNN with this retraining framework that can eliminate the biases that you do not want.
ideally, I would think once you remove sky, because that might have been the most important feature
Yes.
from its original view. Now you remove it. When it's retrained, it should probably put some more kind of learning capacity on other things, and therefore it should get a more detailed model. I mean, in your example, you simply had simpler rules. After you remove sky, you just
Yes.
had simpler rules. But I would think it would just put more detail in detailed rules in the other parts, of
Yes.
the image.
It would. It would if you only specified the bad concepts. I had specified the good concepts as well, which was go towards a desert, sand, or ground like concepts and go away from sky. So that's why the network sort of converged to these good concepts. But if you just specify don't go towards sky, it will find other things there and the rules will become more diverse. It will find other things that can be used for the classification to maintain the accuracy. Yes.
Okay. I'm also curious. Do you want to say a little bit about the jailbreak prevention use case you alluded to?
Yes. So the idea is that can we find certain neurons that can be grounded to particular concepts, right? For example, can you ground a neuron to the syntax being correct in code, for example? There was this famous Anthropic paper where they showed that there are a bunch of neurons they could isolate, which always activate when there's a bug in the code. When you pass in code and there's a bug, this neuron would activate. So what if we could have a neuron, identify a neuron that could always um, activate when the code is correct, for example, and we could ground it. So grounding meaning that no matter what happens, no matter what you prompt, this neuron will not lose its information. Jailbreaking, you can prompt in a way that makes the LLM confused about things. But what if you could mathematically ground that neuron to that particular concept such that this doesn't appear, is what I'm thinking. Yes, and I think we could do it. For example, just an idea is that what if a bunch of neurons that have learned a particular concept, like say only activate when the code is correct, right? This concept. What if this neuron in the attention head is orthogonal to every single neuron that's out there in the transformer, right? That way, this is isolated in some direction that can now be very close to grounded. It won't be affected by whatever things the other neurons are doing because it essentially doesn't share any direction with them.
I mean, very disentangled.
Yes, it has to be very disentangled such that it is not very correlated with the other neurons. Yes, and that way we could achieve this.
Okay, great. Any last minute questions on any of our channels? So, by the way, this time we're getting coverage on all of our channels. This is great as far as questions. Um,
Mhm.
Okay, well, if there are any other students, this is fortuitous, Parth. You're on the job market. Glad we got to give you some visibility.
Yes, thank you so much.
Good luck to you. And any other students out there in a similar kind of position, if you had some papers in top conferences, let us know. We'll give you the spotlight and help you get a job. So in general, the students, postdocs, you are our kind of stars. So you're the future of this field. So anything we can do to help you, let us know. So
Thank you so much. Yeah.
anyone out there wants a little boost or any other way we can help, let us know. Okay, well, thanks so much, Parth. And everyone, reach out to Parth. The universities, you should hire Parth. And
I appreciate the shout out. Thank you so much. Yes.
and Parth, if you have time, maybe jump on the Discord, answer any other questions
Yeah, for sure.
people might have, and who knows, you may find your next 5 collaborators there.
Yes, sounds good. Thank you so much for giving me this opportunity to present my research. I've been following the Nessie Wednesday talks for a long time now, and I don't think I've missed a single one. So thank you so much.
Awesome. No, we exist because of folks like you doing great work. So, okay, thanks everyone, and thanks Parth, and we'll see you next time.
Thank you. Yes. Bye bye, everyone.